Applications in ROS are built around the concept of nodes, which are processes responsible for one or more tasks. They can communicate with each other using topics and services, which we will use to build a number of examples in this course. I will also demonstrate most of these examples using Python and C++, so you can get an idea of how to work with both languages. In the previous episode, we reviewed topics and services, as well as demonstrated how to run a few ROS demos and tools using the command line. My goal was to get you familiar with how topics and services worked before diving into actual code, as you'll be using the command line quite often to test and debug your programs. Now, we'll finally write some code, starting with a publisher and subscriber in Python. Recall that a topic is a named communication channel for passing messages between nodes. Specifically, it relies on a publish-subscribe model where a publisher is an object in a node that broadcasts messages to that particular topic. A subscriber is an object, usually in another node, that receives messages from a specific topic. When you create these objects, you tell them which topic you'd like them to publish or subscribe to. Assuming you publish and subscribe to the same topic, all subscribers will receive any messages sent by the publisher. This is useful for when you need to, say, periodically send out sensor readings to nodes that need them for calculations. One of the advantages of ROS is that messages can be passed among nodes written in different languages. Now, let's actually dive in and write some code. In the graphical desktop for the ROS2 container, double-click on the ROS2 workspace in VS Code icon. That should bring up a VS Code instance. Say, yes, I trust the authors, and I'm going to go ahead and make it full screen. The workspace is automatically configured with some extensions that help us navigate C++ as well as Python. You can see the two different workspaces that are mapped here. The first is our config/workspace. Any code that we save in here is going to be saved on the host machine, so you have access to all the code that you're writing. And there's also opt-ROS Jazzy, which is the ROS2 distribution. You're welcome to look through here in order to get information about the ROS source code. For now, let's collapse that. Go to Terminal, New Terminal. Let's start in config workspace. You'll notice that anytime I bring up a shell instance in this container, it automatically sources opt-ROS Jazzy setup.bash. That gives us access to all of the environment variables and ROS2 tools. If you have ROS2 installed locally, not using this container from the repository, you will need to source that setup.bash file either manually or put it in your own .bashrc so it fires automatically. Go ahead and run that if you haven't already. In the future, we won't need to run this. Just assume that it has already been run as part of this .bashrc script. You should be in the workspace directory. If not, navigate into there. We're going to make a source directory or SRC directory in that workspace. This is where we're going to store all of our code. Let's go into that source directory, and we're going to call ROS2 package create. This is a subtool that generates the folder structure and a bunch of the boilerplate code and files for us, so we can go ahead and start writing nodes in that package. We need to specify the build type, whether this is a C++ or Python package. If you don't enter anything here, this option or this parameter defaults to ament CMake. Ament doesn't mean anything. It's just the name of the build system in ROS2. ROS1 had catkin, and ament replaces that. So if we don't specify it, it will call ament CMake just like this, but we're going to start with Python and then explore C++ in the next episode. So we're going to type ament_Python for our build type, and this should be build, not built. Let's give the package a name. We'll call it mypypkg. That should create the folder structure for you. If you go to the File Explorer in VS Code, you should be able to drop down Workspace. You can see source here, and you can see it automatically generated this package. In the next episode, we'll have mycpp package. That's in the same level source directory as this one. Everything in this directory makes up a ROS2 package. Note that the ROS2 package contains a Python package, which is in this mypy package. We can tell this is a Python package because it has this __ init __ .py file. This tells the Python build and packaging system to treat this directory as a Python package. We can leave this file blank, but it does need to be here. Resource contains a file with the same name as the ROS2 package. Often this is empty. But the name must be the same as your package. This marks the package for discovery by ROS after building and installing the package. You need to have this file here in order to run anything in this package. The test folder is where you can place any sort of unit and integration testing. It also has some of these built-in scripts for style checking. We can ignore those as we're not going to be diving into testing in this series. Package.xml contains metadata for the ROS package, and this is absolutely required for building. It's also where you declare package dependencies. So if your custom package relies on other packages, you would list them in here so that ROS knows how to link them. Setup.py. These are instructions for Python's setup tools. That's a built-in Python tool about how to build and install the Python package, which remember is part of the ROS package. It tells it where to put scripts when installing the Python package in development mode versus install mode. We can leave this alone as ROS will call setup tools during the build process. It will look at this file and figure out where to place your library or your Python package as part of that process. Setup.py, similar to setup.cfg, is used by setup tools. And this is the script that tells it how to build and install the Python package. Here you can list the various Python and ROS dependencies. You also need to put in your various entry points. These are your executables and which function needs to be called in those various executables. This is where your Python code gets connected to ROS-specific build tools. So we will need to modify this file. Let's start by writing our publisher. This is just going to broadcast hello world out to a particular topic. Let's close this file. Let's go to our Python package that's inside of our ROS package. Let's create a new file, and we're going to call this minimal _ publisher.py. I'm going to move this terminal down a little bit so you can see what's going on up here. We're going to import RCL.py. That is the ROS client library that is needed for just about anything we do, because we're going to be calling functions in there and using the node class specifically to write our custom node. We will also be using the RCL.py executors, specifically the external shutdown exception in there in order to capture any events that might occur that say shut down this particular node, and we can use that to clean up resources appropriately. We will also want the node class that's part of RCL.py.node, and we're going to use the example interfaces.msg. From there, we will import that string interface. That's what we're going to be using to broadcast messages to our topic. Next, we're going to define a custom class. We will call this class minimal publisher, and it is going to inherit from the node class that we imported from RCL.py. I'll put a quick doc string here that explains what this node is doing. Then we will write our constructor, which is given by def __ init __. Remember that in Python, when we are writing member functions or methods within a particular class, we need to pass in self as the first parameter always. That way it knows about which particular instance of that class is calling that function. Then we will call the node class constructor. So that is the parent class node, and we are going to provide that constructor with the actual name of the node. The name of our class isn't the name of the node, that's just the name of the class. The node name is assigned by this string we passed in this case, minimal _ publisher. Then we will create a publisher object. This is something known to ROS as part of the RCL.py library. I will use the common Python style to put underscores in front of what's supposed to be private members, whether that's private variables as part of a class or private functions. You don't have to do this. I just like to keep this style so that you know what's supposed to be private versus public. We're going to assign to that variable the object returned by createPublisher, which is a method inside of the node class. We're going to pass in the interface. In this case, it's that example interface's string. We are going to name the topic, in this case, my topic, and we're going to specify a quality of service. This third parameter should be a quality of service or QoS profile. There are various ways to fill it out, but the easiest way is to just specify a number. If you just specify an integer here, this is the depth of the quality of service. In other words, how many messages to keep in the buffer should things back up in that topic or ROS isn't quite keeping up with the messages passing back and forth. So it will queue up to 10 messages. I'm going to go ahead and zoom in so you can see what's going on, especially if you're reading this on a small screen. And I am going to go ahead and hide this panel so I can keep typing and you can see what's happening here. Next, we're going to create a timer. This is another object that's part of the node class. This allows us to periodically call a function. In this case, we're going to set up the timer to fire every half a second or 0.5 seconds. And we're going to have it call the underscore timer callback function, which we're going to define in just a moment. Again, I'm using underscores as a prefix to denote private functions or private member variables. The output of that is a timer object. We will assign that to the self._timer variable so that you can do things like cancel the timer or inspect it if you so desire later. ROS2 has a few functions you can use in order to control these timers, like cancel them and restart them. Next, I'm going to create another private member variable called _counter, and we're going to assign that to 0. All we're going to do is just increment that every time a message is sent out to the my topic. Then we're going to define that timer callback method. To send out a message to a topic, we need to fill out the data or all of the fields inside of the interface that we specified. We imported the example interfaces.message and the string interface that's part of that suite of example interfaces. So we will create a new string object. And inside of that object, we have just one field, that's data, so message.data. And we will assign that to the string hello world and the counter. In this case, I'm going to use a Python F string so that self._counter will be replaced by the actual number that's in the counter. Then we will actually publish that message by using our publisher object that we instantiated earlier. We will call the .publish method in there and pass in that message. Remember that this is an object that is essentially a wrapper for our message data. We fill out the fields and then we can publish that message object. Rather than printing directly to the console, I recommend using the built-in ROS2 loggers because you have access to various levels of debugging severity that you can enable and disable, as well as look at a record of all of the logs, and you can do something called bagging that we won't cover here, but you can essentially set up these long logs and then replay them as if the ROS node was running, which can help things like testing your robot or feeding a machine learning model. In that log object that we get here, we can print a number of severity levels, including info, debug, error, fatal, and warn. So a common one here is to use info. I'm going to use another F string and just say publishing and print out whatever was in that message.data string. Then we're going to increment that counter, and we are done with our node. So a node is just a class or an instantiation of a class that inherits properties from the node class built into the ROS2 or RCL.py, or if we're using C++, the RCL CPP library. Then we need to define an entry point for our node so that when we launch the executable, ROS knows which function to call. We will do this by defining a main function. The first thing we need to do is initialize the RCL.py module. We do that with this .init function, and I'm going to put this in a try block so that we can catch any errors that might occur. We then instantiate our minimal publisher object. This will call that constructor, and we're going to assign this to a node variable. RCL.py has this function called spin. We pass it in our node. That's the node we just created, and it will run that node forever in its own process. If you do not explicitly catch keyboard interrupts for things like Control-C or shutdown requests from other parts of the program or other processes, you will probably have an error in Python. It will just display an error and still exit out of that process that's running this node. which is fine. But if you want to appropriately do that without any errors being thrown, you can use this except block, catch the keyboard interrupt or external shutdown exception. And then for our case, you can just say pass. That means nothing happens. Feel free to print something here if you'd like, or handle those exceptions in some other way. I like to put this finally block in here. Once that node variable goes out of scope, we have to assume that the Python garbage collection system will eventually get around to deleting it, but we don't know when that will happen. So generally, if you want to get rid of a node, rather than just letting your variable go out of scope, it's a good idea to explicitly call this destroy node method. This will ensure that the node is destroyed and resources are freed up immediately. We first check to make sure that the node still exists, because garbage collection might have already gotten to it. If it's still there, go ahead and call this function. Similarly, if RCL.py is still running in the background, if it's still trying to handle things, even though we've asked it to shut down, we can see if it's running, and if so, explicitly call this shutdown function. Let's make sure this if statement has the appropriate syntax. When we define our executable, we will explicitly give it this main function. But if you wanted to run this Python script or Python program from the command line as is without going through the ROS2run process, it's usually a good idea to script in this point that gives it an actual entry point into that main function. So this if __name __ says that if we try to run this script directly from Python or the Python interpreter, it will be given this name main, and it should go ahead and run this main function. Let's save that. Then we're going to build our package, which contains our executable here. Let's go ahead and bring that terminal back up. Looks like I still have two going on here, so I'm going to remove this one and go back to this terminal. You want to make sure you're not in the source directory, so let's go up one, because the build system is going to look in the source directory and then create other directories alongside it. We're going to use callcon build. Callcon stands for collective construction. It's a build tool for ROS2, and it can be used to build multiple packages at the same time. If you're coming from ROS1, this replaces catkin make. So that tool is no longer available. Instead, we have callcon. It's useful for not only building packages, but also installing and testing them. So if we say callcon build, it will build any packages it finds in that particular directory. Right now, we only have one, mypy package. This should finish with no errors. If you look in the workspace tool, you might have to refresh the files here. You will see build. This is any compiled objects and intermediate files used by callcon during that build process. You also have the install folder. This is executable scripts and binaries, any shared libraries you might have made, and any message interfaces that are unique to your particular package. We will explore creating custom interfaces later. And then you also have log. This is a log of any builds and tests that you might have run as part of that callcon process. Notice again that these three folders are created alongside of this source directory. So within source, you will have your variety of packages that you might create in here, and then those get built and bundled together, and callcon uses these three folders to make that happen inside of your workspace. So note that in ROS2, you could have multiple workspaces for various projects you might be working on. And in each of those workspaces, you can have multiple packages. And in each package, you might have multiple nodes, libraries, or executables. So I hope that makes sense. The difference between a ROS workspace, a ROS package. Inside of that ROS package, you might have a Python package or a C++ library or C++ executables. So that's how ROS breaks down your source code and then creates executables and libraries from that. Let's head to our other desktop. We're going to go to workspace 2 over here. In the previous episode, we mentioned that we will use VS Code to write code and build it. And then we will use the second desktop to run and test our code. To run our executable or our node, we will call ROS2run, give it the name of the package, mypy package, and the name of the executable. This is minimal publisher, the name of that node. However, you will likely find that you see this error that says package, the name of your package is not found. That's because this particular shell does not know about my.py package. We've already sourced the ROS2 environment. By default, that's in that .bash rc file, but we have not sourced the environment needed for our custom workspace. So we want to head to that workspace. In there, you'll see your various folders. Take a look inside of that install folder, and you should see another setup.bash. So we need to call both the ROS2 setup.bash to give us access to both the ROS2 environment, as well as those default and example packages we have been testing with in the previous episode. And we need to source the setup.bash inside of our workspace to give us access to our custom packages. So we're going to call source install / setup.bash. Now let's try to run that again. So I'm going to push up a few times. I've got ROS2 run, the name of my package, and minimal publisher. Uh-oh, another error. This time it says no executable found. So we're making progress, but you are seeing that we need to do a few more things than just write some code for our package. When you see no executable found, it either means you misspelled the executable name, or in this case, we forgot to register the name of our executable as part of that install process. We'll head back to our code, and we need to go into setup.py. Scroll down, and you should see a field for entry points. This is where we will list the name of our executable and where ROS2 should find it. So in this console scripts, we'll create a string. The first part of this string is the name of the executable. This is what we will actually call when we say ROS2 run. Note that it can be different from the file name. Then we will say equals to set it to the actual entry point. We'll give it the name of the Python package, in this case, my.py package. Then we'll give it the module path. So we have the name of the package, and then we will give it the module. This is something similar you would do in, say, Python, where you would say import my.py package.minimal publisher. For this, however, we need to give it an actual entry point, and this is the name of the function found in that file. For this, we're just using main. I like to list a trailing comma here so that it's easy to add console scripts in the future to this array. Let's save this with Control S. If you build this, you will likely find that minimal publisher will now run. However, ROS generally wants us to include any dependent ROS packages in this package.xml. So let's open that. Somewhere after license, you can do this before test depend or after test depend. I like to do it just before. We will use XML tags to say depend, and we can list our ROS dependencies here. The first one I will list is RCL.py. Notice the XML tags where we say depend and /depend to close that tag. This tells ROS that we are depending on the RCL.py package. In my experience, things will build and run fine without listing them here, but it's generally considered best practices to list them here to explicitly let ROS know that we are depending on these other ROS packages. The other ROS package that we need for our Python code is example interfaces. With those two set, let's save with Control S. I'm going to say callcon build in order to build this package, but I'm going to add an extra argument here. When you say callcon build, it builds everything under that workspace. If you have multiple packages in that workspace and you only want to build one, this might take some extra time you don't want. So we'll say -- packages select, and then the name of the package or packages you want to build, and they're just separated by spaces. In this case, we will say my.py package, press enter. With any luck, this should build, and because of that ROS extension, it will give us this green pop-up to let us know that everything was okay. Now let's go back to our run desktop, and we're going to enter ROS2 run, my.py pkg, minimal publisher again. Note that we don't have to source again. Once you've sourced in a shell, it will know about that package. But if you add new packages, and sometimes if you add new libraries or executables, you might have to resource. The name given here is the name of the executable when you run ROS2, run my.py package, and then this name, so minimal_pub. It will successfully run the main function in your minimal publisher.py file found in the my.py package. This is the Python package that's located over here. However, in many cases, you will find that this executable name is the same name as your Python file. So we'll leave it as such. We will save with Control S. You can call callcon build. That will build all packages found in that workspace. If you don't want to wait that amount of time, you can say --packages-select and give it the name of the package or packages, separated by spaces, that you wish to build and build only those. In this case, we are going to build only my.py package. Hopefully that finishes without errors. The VS Code extension, ROS2 extension, will give us this pop-up to say that it built successfully. It should be green. If you see yellow or red, you should look into those warnings and errors. With that, let's switch over to our run desktop, our running and testing desktop. Because we have already sourced that environment, this shell should know about that environment and be able to run things from our package. So try running that. And sure enough, with any luck, you should see it publishing this hello world and the counter value out to that particular topic. Let's bring up a new terminal. And here we're going to type ROS2 topic list. You should see my topic. That's the new topic we just created from that node. You can get information about that with ROS2 topic info. You can see the type being used, and we can use ROS2 topic echo in order to print out anything it sees, because this acts as an immediate subscriber to that topic. Press Ctrl-C to exit out of that, and we will exit out of this one as well. Now we will create our minimal subscriber so you can see how the listener side works as well. Inside of our Python package, in our my.py package ROS package, let's create a new file. Call this minimal_subscriber.py. We are going to import the exact same libraries that we did in our publisher. So we need rcl.py, we need rcl.py.executors. From that, we'll import external shutdown exception. We'll need the node class and the string interface from example interfaces. Then we will define a minimal subscriber class that is a subclass of node. In that constructor, we will explicitly call the node class constructor with our desired node name, in this case, minimal subscriber. Then we will create a subscription object. The node class defines this create subscription function that instantiates that object for us. We will give it the interface we want to use, in this case, the example interface's string. We will give it the topic name we want to subscribe to. This should exactly match the topic name given in the minimal publisher example. We will give it a callback. This function is called whenever something is published to that topic, and the message received will be passed into that callback. Finally, we'll give it that QoS profile, in this case, just the depth, so it will store up to 10 messages in a queue. Next, we'll define that listener callback method. Note that the callback given in the create subscription function is required to have this second parameter, this message parameter. Actually, it's the first parameter because self is just kind of assumed to be there as part of this method. That message is passed in. That's how we can have access to the message received on that topic. All we're going to do is just get that logger object and print out to it using the info severity level received message and then the data in that received message. Next, we're going to define the main entry point. I'm going to remove this terminal for now so you can see what's going on. Just like we saw in the minimal publisher example, we are going to initialize rcl.py. We're going to create the minimal subscriber as our node, and we're just going to say spin, which just means run that node. If Control-C is pressed or we have some sort of shutdown request, go ahead and catch that. We're not going to print any errors to the screen, and just continue along to the finally block. As we saw previously in this finally block, if the node still exists, go ahead and destroy it. That way it happens immediately. And if rcl.py is running, we will tell it to explicitly shut down. If this Python program is called directly from the command line without going through ROS2 run, we will say go ahead and run main. This part is probably not necessary, but it is handy to have. Let's save that. Let's say view terminal to bring up an existing terminal. And remember, before we build, we actually want to go into setup.py, and we need to add it to our console scripts for our entry points. Just like we did for the publisher, we're going to say minimal subscriber equals my.py package.minimal subscriber, and then the name of the function after that colon, so main in this case. Notice I'm putting a comma at the end here, so that's easier to add new lines. Python just ignores these trailing commas for these types of arrays or lists. Don't forget to save this. I'm going to press up, so call con build, packages select mypy package. With any luck, this should build. We got the little green icon here. Let's go over to our run desktop. Let's run that publisher again in the terminal on the left. And we're going to try to run this minimal subscriber on the one to the right. Once again, you see mypy package is not found. That's because we need to source the install setup.bash script that's found in config workspace. Now we should be able to run that minimal subscriber. Any messages being printed or sent out to that my topic by the publisher will be received by this minimal subscriber. And it's printed out here, received message, hello world, and the number should line up with what you see on the left. Let's bring up a third terminal. And I'm going to run rqt_graph. Here you should see your minimal publisher and subscriber and how they relate to each other. The minimal publisher is publishing messages on my topic and being received by this minimal subscriber. If you'd like to learn more about the RCLPy API, head to docs.ros.org/en/jazzy/p/RCLPY. Here you can read about all of the various functions and data available to you in RCLPy. Specifically, we were working in topics, and we were creating a publisher and subscriber. So if you go into publisher, you can see all the functions that we were working with. For example, when we created that publisher, and then we could call .publish. In addition, we created a subscriber, and we gave it this callback. Feel free to refer to this documentation as often as you need as you're learning to use ROS2, especially these ROS client libraries. I hope this helps you see how to write a very simple node using Python. Don't worry if some of the concepts and tools are still a little nebulous. We will be practicing with them throughout the series, including subclassing, setting up callbacks, building packages, and running executables. Next time, we'll repeat this same exercise using C++ instead. See you then.